Welcome to this episode of Mentors at Your Benchside, the podcast giving you advice, tips, and tools for getting the most out of your research. I'm Eva Amson, and today I'll be talking to you about using OD 600 measurements to find out if your bacterial culture is still growing. This episode is for anyone who has ever wondered, how do I know when my bacterial culture is done growing? When should I harvest my cells? We'll talk you through the bacterial growth curve and tell you how to check what stage your culture is in using OD 600 measurements. Let's start by reviewing the 4 basic phases of a bacterial growth curve. Now, if you look at the article that's on our website, which you can find in the episode description, you can see a figure of the growth curve, and it shows the 4 stages. First, the lag phase, where the number of bacterial cells is very low. Then the log or exponential phase, where it increases, the stationary phase, where the number of cells stays high, and finally the death phase, where the number goes down. A fresh inoculation of bacteria into culture medium starts out in the lag phase, where cells are metabolically active but not dividing. During this time, cells are adapting and adjusting to their new environment. The bacterial culture then enters the log phase, where cells rapidly divide, normally by binary fission, and double in number over a given period of time. For example, E. coli can double every 20 minutes in log phase. Growth during this phase is exponential and metabolic activity is uniform across cells. Bacteria in this phase are also most susceptible to antibiotics, for example, making it the ideal phase for research work. And when a maximum cell density in a liquid culture is reached, cells enter the stationary phase. During this phase, there is no overall increase in the cell population. Cells that die are replaced by newly dividing ones, but the overall number of live cells stays the same. If you're working with spore-forming bacteria, this may be the stage where vegetative cells sporulate or form new spores. And finally, the death or decline phase occurs due to a variety of factors, including a lack of nutrition or oxygen, a change in media pH as a result of cell metabolism, or an accumulation of toxic cellular waste. Now you can use OD 600 measurements to determine your bacterial culture growth stage. Measuring the OD 600, or the optical density at 600 nanometers, is the easiest way to gauge the bacterial culture growth stage. Optical density measures the degree of light scattering caused by the bacteria within a culture. The more bacteria there are, the more light is scattered. The 600 nanometer wavelength is specifically chosen for bacterial OD measurements because, unlike UV wavelengths, 600 nanometers is not harmful to the culture. This wavelength is also not usually absorbed by the yellowish media like TSB, tryptic soy broth, and LB, lysogeny broth. By monitoring the rate of increase in OD 600, you can identify the lag, log, and stationary phases of a bacterial culture. So how do you take this measurement? For a simple suspension of cells in liquid, you first need to zero or blank the spectrophotometer with fresh, uninoculated medium to subtract any absorption contribution the medium has on the measurement. Then take a sample of your culture and measure the OD 600. When measuring the OD 600, there are a few things to watch out for. First, when you pull a culture sample, ensure that you've mixed it well and take the measurement right away, since cells can begin to settle within a minute or so, which leads to inaccurate results. If your bacteria form biofilms or aggregates in solution, this will severely affect the accuracy and precision of your measurement. In this situation, you might need to sonicate or further process the culture to break apart these clumps. Check the literature regarding the bacterial strain you're working with to avoid or negate this problem. And most importantly, an OD reading that's larger than 1 is not accurate. OD readings this high are beyond the dynamic range of most spectrophotometers, meaning that the readings do not increase linearly as cell concentration increases. If you do obtain an OD reading higher than 1, dilute your sample twofold or more until it reaches an OD 600 that's less than 1. Now, the OD 600 is not an absolute value. The OD value represents the amount of light that is scattered by your sample, but that value is affected by the intensity of the light beam in the spec and the spec design. This means that similar samples will give completely different OD values in different specs, owing to the specs having different bulbs, or even in the same spec over time as the beam intensity reduces with the age of the bulb. So recording an OD value in your lab book doesn't really mean anything, as this number is as much dependent on your spec as on the density of your culture. What you really want to know from an OD 600 reading is the density of the cells, for example in cells per milliliter. And to get this, you need a standard curve. In other words, like any other spec-based experiment you will ever perform, you need to calibrate the absorbance value against the number you actually want to know. Constructing a standard curve for OD600 is a bit tedious, but it's a good exercise to go through every 6 months or so and for each spec you use. You start by making a suspension culture of the cells you're interested in, and then diluting it to obtain a series of samples with ODs of 2, 1, 0.8, 0.6, 0.4, 0.2, and 0.1 on your spec. Now don't make serial dilutions, as these are very inaccurate. For each OD, you then want to know the cell density in cells per mil. So for each OD, make dilutions of 1 in 1 times 10 to the 7th, 1 in 1 times 10 to the 6th, and 1 in 1 times 10 to the 5th. Then plate 1 mil of each onto suitable plates and grow them up. Then count the number of colonies that are formed on the dilution that gives the most appropriate number, so the one that's most easy to count, and multiply it up by the dilution factor to obtain the number of cells per mil in the original sample. These values can then be used to construct a calibration curve of OD versus cells per mil. The conversion factor for your spec, so the number of cells per mil represented by 1 OD unit, will be equal to the gradient of the linear portion of the curve, normally up to about OD1. You can now use this factor to convert your OD reading to cells per mil, and as long as you calibrate whatever spec you're using in the future, this number will be absolute and comparable between experiments, specs, and years. But just when you thought it all made sense, a word of warning. Since the OD of a sample is dependent on the size and shape of the particles in it, different cell lines can have completely different relationships between OD and cells per mil. This means that a separate calibration will be needed for each cell type you use, which is tedious but better than recording meaningless and arbitrary numbers in your lab book. And if you work with flasks to grow bacteria on a regular basis, it's helpful to train yourself to estimate OD by eye. This way you can save valuable time by skipping OD 600 checks when flasks are clearly not within the OD range you're looking for. It doesn't replace OD 600 entirely, but it can help you cut down on the number of times you need to measure the OD 600. You might also want to consider using a microplate reader to increase the throughput of your OD measurements. Besides OD 600 measurements, there are also other methods of monitoring bacterial culture growth and metabolism. Even though monitoring growth using a bacterial culture's OD 600 is a tried and true method, there are several other ways to assess the growth and metabolism of bacterial cultures. You may find that some of these factors are more relevant or useful for your specific application too. One of these methods is imaging. By taking samples of your culture and checking them out under a microscope, you can begin to get a sense of the approximate concentration of live cells in your culture. As a bonus, you can compare images of cells to see if there are different morphologies from batch to batch, or how many vegetative cells are in a spore-forming culture. Another method is looking at dissolved oxygen and carbon dioxide. Consider beer made from yeast, or kombucha made from yeast and various bacteria, and other enjoyable beverages fermented by microbes. As the fermentation progresses in these examples, oxygen is consumed and carbon dioxide is formed. The same process happens in an aerobically growing bacterial culture. Dissolved oxygen and carbon dioxide probes are commonly used in bioreactors. If you want a less invasive option, you can get optical sensors and patches that use LED fluorescence to monitor dissolved O2 from outside a flask. Another method is by looking at the pH. Most bacterial species lower the pH of their media over time, including E. coli. For some species, acid production can actually limit a culture's maximum growth and viability. Like oxygen sensors, methods exist to continuously monitor pH non-invasively in flasks. And finally, another method is sugar analysis. With certain instruments, getting a fast and reliable measurement of residual sugars from your growth medium is possible. For instance, if the primary carbon source in your medium is glucose, obtaining a glucose measurement midway through bacterial growth can provide a sense of where the culture is in the growth curve. So, when should you harvest your culture? In short, it depends entirely on what the end goal is for the culture. For instance, if you're working on extensively growing and inducing E. coli to overexpress non-native proteins, which would then be purified from the culture, you might find that the quality and quantity of protein you obtained from the culture depends on the phase the cells were in when you harvest them. In other cases, however, the goal is to simply harvest as many cells as possible. Once you know the specific growth phase at which you need to harvest cells, be sure to perform a couple of test runs, including measurements, to make sure you are correct in your assessment of the bacterial growth timing. This will give you a strong sense of how long it takes for your culture to be ready to harvest and provides historical data for comparing bacterial culture growth curves. Always start from a smaller seed culture to get reliable and consistent growth in flasks. Finally, test your cell culturing techniques a few times until you're comfortable to reduce the risk of contamination. From the relatively simple OD600 measurement to metabolite analysis, there are a plethora of ways to keep tabs on your growing bugs in the lab. Because the growth stage affects much within a culture, knowing how to accurately measure this parameter is a key technique in any bacterial lab. So that's it for OD600 measurements and bacterial growth curves. Check out the episode description for links to related articles and resources. And don't forget to subscribe to the podcast to get more help and advice from mentors at your bench side.